hypothesis that I will actually need for the entire of the talk, I think, is that C has nothing in arity 0 or 1. So in arity 0 is 0, and in arity 1 is the ground field K. And so let me remind you just this construction that we did yesterday, which concerned convolution. So let A be a P algebra. So equivalently, this is the same thing as saying that this can be expressed by as a morphism into the endomorphisms operad of A. And since we fix this data, I can just compose this with a map from P infinity, which just represents the fact that we can forget that A was a strict P algebra, and we just remember that it is a homotopy P algebra, say P infinity algebra. We'll pull back along the we restrict the scalars here, and from this. One can so let me call this map mu, and from this we consider the Lie algebra that I denote by G P infinity A, which is a certain totalization of the following sort. So it's this product from n equals 1 to infinity of hom of C to the endomorphisms of A. So hom, the symmetric maps in every possible arity. Now we realize that this is exactly the convolution of the operad C with the co-operad C with the operad A, and we're taking this totalization. The invariants of a hom space are just equivariant maps, and this Lie algebra, what we saw yesterday still, is that the Maurer-Cartan elements of this Lie algebra are exactly the P infinity algebra structures on the chain complex A. So the map that the structure map that I fixed, this representation of P infinity, is just interpreted now as an element here. So the Lie algebra that we actually want to have in mind is sometimes this is called the deformation complex of the actual. So what's our goal? We're actually trying to deform the algebra structure on A, and this is governed not by this Lie algebra, but by the Lie algebra G. P, maybe I should call this P infinity because it governs P infinity structures on A. So G P infinity A twisted by this Maurer-Cartan element mu that that arises from the algebra structure. So just maybe a slight historical remark. People do tend to call this deformation complexes, but I think just because originally we would see complexes arising of this form, maybe non-operadically, but just we would just care about their homology maybe, but it's actually quite important that we look at this as think of it as a Lie algebra. Just another remark, which is yesterday I mentioned that this is actually admitting a stronger structure than just a Lie algebra. It's a pre-Lie algebra. This is not preserved when you twist by a Morcartan element. So it is still a Lie algebra. Lie algebras are twistable by Morcartan elements. Pre-Lie algebras, not. So the structure that exists here is this as a DG LA. Just to ground ourselves somewhere, let's just do one quick example to see that somehow we've already seen these objects in maybe a different form. If it's the first time you're seeing this, so let's suppose that A is an associative algebra. So to fit this context here, I want to consider an A infinity, the infinity algebra. I need to fix its causal dual C. That I remind you, C here is the linear dual of A, but with a certain degree shift that I hope this time Bruno will not be too mad at me for denoting it with these accolades. But it's this shifted version of the associative operator. Now, if you just compute what this maybe seemingly looking complicated expression, you just see that G A infinity A is, well, what is this? In arity n, Cn is just the representation, the regular representation of the symmetric group Sn, but with a degree shift. So this in degree 1 minus n. So I remind you that my conventions is that differentials are going up. So this is the degree that we need to take. So if you just compute this, you'll see that these are sigma invariant maps from the regular representation. So it's just identifiable with the target, but with this appropriate degree shift. So this is Om tensor n with to A, and you'll and after twisting, sorry, yeah, this in degree 1 minus n. So this upon twisting is just the Hochschild is exactly, or maybe up to a degree of 1, a degree shift of 1, the Hochschild complex of the associative algebra A. So just to mention that these constructions, they recover very classical objects such as the Hochschild complex, and if you just plug here the 3 classical cases of Lie algebras, and associative and commutative, you recover the Chevalier-Lemberg complex, the Hochschild, as I just mentioned, and the Harrison complex. So it might not be just 100% clear yet why this represents deforming around the point A. But so if you just as an example that maybe also connects with this with what I said in the very beginning of the introduction, if you want to deform the associative product on A, maybe one of these formal deformations, it would correspond to finding a certain associative product in a formal power series on A, such that when you evaluate back on h bar equals 0, you get back the product on A. So this corresponds exactly with Mark-Cartan elements on this G infinity A mu tensored up with our space of parameters, so K of H bar, and since you don't actually want to do anything to the original product that you had there, you just have to mod out by the identity K leaving here. So this will be a first instance of the actual deformation functors that we'll be taking a closer look at tomorrow. Also, another convenient thing that the operatic calculus buys us in this example is functoriality. So maybe let me write it in an example. So there are maps of operads from the operad Lie to the operad associative to the operad of commutative algebras, which just represents the fact that commutative algebras, you can forget that they were commutative and they're associative, and that if you have an associative algebra, it induces a Lie algebra by commutativity. So this sequence in particular squares to zero. The composite is zero. And this descends to the Lie algebras. So concretely, this gives maps of Lie algebras from G C infinity A to G A infinity A to G L infinity A. And let me just point out that this C is not actually this com. This C is because it's the dual of Lie that gives C infinity. So taking the Mark-Cartan taking Mark-Cartan elements on each of these guys will tell you just that C infinity algebras are sent to A infinity algebras, etc. Yes. Yes. So in the middle there is a map of cooperats from dualizing all of this.
Maybe you can write it between your two lines. Between your two lines, entre les deux lignes, tu peux écrire le morphisme de coopérate au niveau du dual de cosine. Ça éclairera le morphisme de données quadratique, donc un morphisme entre les dual de cosine. Et ça va devenir anti-Schlick, Verras anti-Schlick, comme anti-Schlick.
Yes, but sure. But specifically, this arises from. Sorry. Yes, exactly. So by dualizing this is com-dual to. Yeah, I know this is not exactly what.
The other direction.
De toute façon, c'est contrat.
No, this is fine. So you take this. Okay, then you shift. Then you shift this, and then when you go down here, the maps of cooperats up there induce maps of cooperats in these deformation complexes. So what was I saying? Oh yeah. So now you can take Mark-Cartan elements, and you get for instance. And then you can twist. So Mark-Cartan is comparable to Mark-Cartan is functorial. Twisting is functorial. So what you would get is if A is a com algebra, via Mark-Cartan element mu. what you can do is G C infinity on A, mu gets, you can just twist on both sides, and this is what you get. There's nothing magical happening here, but it just, so one, it recovers exactly the usual inclusion from the Hochschild complex, sorry, of the Harrison complex of the algebra A into its Hochschild complex, and more maybe deformation theoretical perspective on this morphism is deforming, trying to deform a commutative algebra, but as an associative algebra, as an associative algebra. Okay, questions here? So now I want to talk more and more about Moore-Cartan. So a bit Moore-Cartan in more detail. I'll have to talk about the gauge group to go any further. And the idea behind this is that over the real numbers in differential geometry, there is this Lie correspondence that tells you that from Lie groups you can get to Lie algebras, but but you also have correspondence in the other direction. So given a Lie algebra, you can integrate it into a Lie group, and the idea, so this is Lie's third theorem. The idea is to have something similar here, but more formal for for not just for classical Lie algebras, but for differential graded Lie algebras, and well, furthermore, without the requirement of working over R. So for any field of characteristic 0, and so the idea is, okay, let's just take assumptions on G. Now G, any Lie algebra, not necessarily arising of this form, but with the condition that G is positively filtered and complete with respect to this filtration. So there is an F1 of G that, so the filtration is increasing, and it's complete with respect to this filtration. In these conditions, we what would we like to do? We'd like to from G, maybe we can restrict to degree 0 elements. Otherwise, if we start exponentiating things with the elements that are not in degree 0, we'll run into some problems. So we want to have some sort of exponential map from G0 into something that I would like to call the exponential group of G. So exponential group. And what we would like to do is to send an element x in this Lie algebra into the exponential of x, which would be defined in well, by the formula of the exponential. But of course, this a priori does not make sense unless G comes from the Lie algebra structure on G comes from an associative algebra structure. So the best one can maybe do if G is a general Lie algebra, differential graded Lie algebra, is to see this landing in okay, and sorry, and then here there would be a natural product. this would converge because of the completion property, and this would be our group. Now, if this does not come from an associative product, the minimal place where you can actually write a formula like this is the universal enveloping algebra of G. And we wish to have a product, wish to have a product.
Just to tell you on the chat, there is a question about the same thing. We don't need this to be finite dimensional. You control the convergence of all the series by your complete
Yes,
equation.
yes. So right, I mentioned that we want. So it's not just that we're dropping characteristic. Sorry, ground field R, and we're also dropping any finite dimensional assumption. So this is not necessary at all. So our wish is to have a product, and the spoiler is that the product, we'll call it BCH. So for Baker, Campbell, Hausdorff. That satisfies some stability with respect to multiplying the exponentials in this universal enveloping algebra. So BCH of X and Y, and the proposition due to I guess this group of 3 people is that a universal BCH formula exists. And since I'm being a bit not completely formal until now, let me just give you both the idea of the proof and maybe clarify a bit what I mean by this. So what one can do is consider the formal power series on 2 elements, X and Y, and you so it's complete. You allow infinite products, and there is a map from the formal power series of X and Y into the formal power series of X and Y, which is exactly this exponential map, which sends you X to the formula above, EX. And what this map satisfies is that exp induces a bijection from the primitive elements So I think Damien mentioned this yesterday, but I recall that primitive element is an element satisfying D of primitive equals 1 tensor the primitive plus the primitive tensor 1 into the group-like elements. So, any questions? So elements satisfying this, and group-like elements, as maybe the name indicates, they are a group, and it actually just turns out that group-like elements on this side is exactly just it's the image of the exponential. It's anything that starts with a 1. It's a 1 plus something in higher degree. And primitive elements are exactly the elements that can be generated by Lie words on X and Y. So it's the free Lie algebra on X and Y, or that would be the case if I were just considering non-commutative polynomials. It's actually infinite words on infinitely words on X and Y, such that you use more and more X's and Y's. So essentially, and so that's it. So essentially, this is telling you that the product over here can be expressed purely, since this is a bijection with inverse the logarithm. You can express a multiplication of, well, you can transport the product that exists here into the product over here, and that's the product you would call the Baker-Campbell-Hausdorff product or formula. So just BCH of X and Y will, it's hard to write a complete formula, but it starts like this. It starts with X, then plus Y, then it has XY, and then it has elements that grow in the size of, in Lie size, let's say. And we denote, so we denote by exp of G, so the gauge group, which is, as I just said, so something whose elements, whose underlying set of elements is just G0, but here you have the group structure given by the BCH formula. And just to distinguish X seen as an element of the Lie algebra and X seen as an element of the Lie group, I will still denote the elements of the exponential group, which in principle should just be X, but I will denote them by EX to insist on the fact that these are seen as objects in this group. Now it turns out that there is an action. So you know that in the usual Lie story, the Lie algebra acts on the Lie group via the adjoint action, and here there is a similar thing. So there is a group action from exp of G into the Morra-Cartan set of G.
Sorry, Ricardo, I don't fully agree with the analogy because I mean, in the Lie group is kind of, I don't know, also having only one Morra-Cartan element, right? And the joint action is just the group multiplication. So
yeah, I agree. I'm stretching the action too much. So the point is that here, secretly, this is actually a simplicial set. It has higher. Yeah, exactly. It's a groupoid. Anyway, this will be mostly the talk of Alexander. But I agree. Maybe it's not the greatest analogy.
The better analogy is connection on principal bundle.
Right. So Bruno says that the better analogy is the connection on a principal bundle.
This is the best analogy.
Okay, but still, the action is still given by some sort of adjoint action, and so I just need to give the formula. So if I have an element E lambda, is it still visible like this? So
you can write bigger.
If I can write bigger, it's better. I agree. Oh. The camera, it seems okay. You really see the whole black line.
No, we see the whole and
yeah.
well.
So the action is given by so on a Morra-Cartan element X, you so you integrate. I mean, heuristically integrate the flow of a formal vector field produced by this, and the actual formula is the exponential of the adjoint action of lambda minus the identity divided by the adjoint action of lambda applied to the twisted differential on, so X is a Moore-Cartan element, so you take the twisted differential of lambda. So the formula becomes just, yeah, so it looks like this because of essentially remarks that I made about how the tangent bundle changes. Well, let's just take maybe for granted that it's an action that involves the exponential of the adjoint. And what we're actually interested of interest is actually the Moore-Cartan set of our original Lie algebra G modulo by, so I'll write just for shortness modulo tilde, but so this is the orbit set of under the gauge action. So this is up to the gauge equivalence induced by this group action. So we should be seeing this as some sort of moduli space. Now, maybe more relevant for the next talk, I don't think my next talk, but literally the next talk, is that one can also denote this by pi 0 of this Moore-Cartan set of G, maybe something a bit more refined, and secretly that's just more structure on Moore-Cartan, and you can see this as some connected components of some Kan complex. But so yes, what we need to retain is that we're not only interested in the Moore-Cartan elements, but up to this gauge equivalence, and this is actually a very well-behaved notion up to homotopy. There's various nice results that tell you that this is well behaved homotopically. Probably the best known of them is the Goldman-Milson theorem. Okay. Really? Okay. The Goldman-Milson theorem that tells you that if G and H are such Lie algebras, so complete DGLAs, and you have a map G, so a map F from G to H, inducing quasi-isomorphism, sorry, an isomorphism at the level of the homology, not of G and H, but so they're filtered objects. So at their respective associated graded algebras, Lie algebras. Then this is compatible with this gauge equivalence that I said, in the sense that then the Moore-Cartan elements of G modulo this gauge equivalence are in bijection via F by with the Morra-Cartan elements of age modulo gauge equivalence. So in practice, this is a very nice result because it allows you, if somehow your Lie algebra, so the way in practice you use this is that you're interested in some deformation Lie algebra, and you realize that, oh, it's actually quasi-isomorphic to something smaller. I still retain somehow all the same information from the deformation theory perspective, because you would still like to consider deformations that are gauge equivalent. You want to consider them the same. And it's even a little bit better than this. It's I can even just replace it by an infinity morphism. So and it still holds true. Sorry. Any questions? Sorry, G0 is the zero element, right? Yeah, just degree zero. Yeah, not zero element. Degree zero elements of G. So of course, formulas like this would not even make sense if you don't take X to be an element of degree zero, because this would not be homogeneous. You'd have something in degree zero, then one, then two. Right, but then in the universal, yeah, maybe one. Forget about the remark concerning one, but yeah. So if you see this as so if you see this as a graded unit, you can see this as a graded unital associative algebra, but indeed, in any case, this will fully land on the degree zero part of the Lie algebra. I don't know if I answered the question properly. Okay. Degree and filtration weight are not related. So I said that. So the conditions that we require is that, well, as usual, the bracket of things of degree A and B end up in degree A plus B, but also you require the same thing for the filtration. Things, if you bracket something in degree P and in degree Q, you end up in degree P plus Q at least. In filtration degree P plus Q. Yes, that's I think all I want to say. So in particular, that's why infinite brackets do exist, because since by definition everything is in degree at least one, in filtration degree at least one, and you keep on bracketing as long as the length of the bracketing increases, then you know that your filtration degree goes to infinity, and by the assumption of completeness, this element exists. So yeah. So how much time do I have? 50 minutes, right? Now I want to use this to go back to just algebras over an opera and present the following general question, or I guess problem. Given P algebras A and B, are they quasi isomorphic? So I will denote the relation of quasi-isomorphism by A tilde B. It's the only relation that we want to consider, but as it has already been mentioned yesterday in both Alexander's and my lecture, there the relation of being quasi-isomorphic to actually be an equivalence relation, you actually need to ask not for a direct map, rather for a zigzag of maps that are quasi-isomorphisms connecting A to B. And so this expressed like this problem is a priori very complicated, right? If you're given A and B, you cannot expect to be supposed to test all possible zigzags of maps between A and B to see if they're quasi-isomorphic. There is different ways to approach this question. One of them would be, well, using model categorical remarks and taking resolutions, trying to lift quasi-isomorphisms. The one I'll actually use, so this will be a bit of a recollection also of what was seen in Alexander's lecture, is the homotopy transfer theorem. Let me just point out that kind of a sub problem of this problem, which is already very difficult. In particular, so given A, is A quasi-isomorphic to its own homology as an algebra? So this property is called formality, and it's not particularly easier to address in general than the first one. Well, maybe a bit, but it's still a very complicated problem. So let me remind you that there is the homotopy transfer theorem that tells you that given A, you can A with a, and you fix some sort of deformation retract or contraction to its homology. So you have some choice of projection, some choice of injection, and some homotopy with some appropriate properties. So the main one is that they're all quasi-isomorphisms. Well, these all exist. This gives us a p-infinity algebra structure on HA, such that A is equivalent to HA, but with this p-infinity algebra, structure acting here. So in some sense, formality. Sorry, I'll try to write bigger. Formality corresponds to some sort of homotopy triviality of this action here. This can be and will be made a little bit more precise. Yes, it's the homotopy transfer action that Alexander mentioned yesterday. I was yeah. So it's the one induced from the transfer. Right. So a consequence of this, I guess a corollary, is that the quasi-isomorphism problem can be in a way simplified. So you have that A is equivalent to B as P algebras if and only if there exists there exists an infinity, P infinity infinity morphism, sorry, quasi isomorphism from A to B. And the reason for this, so one implication is actually independent of the homotopy transfer theorem. So this one is this implication is just you take A, you can resolve it by bar co-bar of A, and an infinity morphism is exactly a map from bar of A to bar of B. But then you take the adjoint of this map, and this is exactly what you get. So in particular, it tells you that every zigzag can be reduced to the smallest non-trivial zigzag possible. And in the other direction, if you have A and B that are connected by a quasi-isomorphism, what you can do is that A. So we've seen that A and H of A are quasi-isomorphic by an extension, the infinity extension of this map P. So let me call this P infinity. Now, if they are quasi-isomorphic, in particular, their homologies have to be the same. So, or they have to be isomorphic. And then you have here H of B, and then there is an infinity morphism all the way back into B. So this is one way of converting infinity morphisms, zigzags into infinity morphisms. So in particular, the quasi-isomorphism problem admits a nice reformulation. Which is, does there exist just an infinity quasi isomorphism from A, from let me just write some conditions. So it's recited in the following way. So given two P infinity structures, so alpha and beta on a space, on a graded vector space on H, does there exist an infinity morphism from one into the other? And it turns out that now we can actually take advantage of, so this has two advantages. So first, you no longer have to consider two different spaces. You reduce everything to a space. This space, by spaces, I mean complexes. You reduced to a single complex, so it's somehow easier to study endomorphisms than just general morphisms. And furthermore, this complex is just the smallest possible. It's the homology. And since you're in the homology and there's no differential, actually being a quasi-isomorphism.
So yeah. What you're saying is, so we want to look at this problem, so we kind of, so a prerequisite in order to have a quasi-isomorphism between A and B is that the homologies are isomorphic as graded vector spaces.
Yes.
So we go to
I guess I need to, okay. I should have said that the first hypothesis is that their homologies are isomorphic, because if they're not, then I mean, it's the only time that this question is easy to answer, but thank you for the remark. I meant to say this. So the only simple criterion we can have for the quasi-isomorphism problem is if the two algebras have the same homology, because if they don't, well, it's over. So we're working always with this hypothesis. And then under this hypothesis, indeed, you can transfer two structures into the same space. Thank you. Anyway, the point I wanted to make is that now it's even get further simplified, because quasi-isomorphism just means isomorphism, since there is no differentials. And actually, because we identified the homologies, we can even suppose that so H is identified with H via the very first map of this infinity morphism. So so we can suppose that F1 from H to H is the identity on H, and this is what people call IE. F is an infinity isotopy. I don't know if this terminology was coined by Bruno or
Under a suggestion of Sullivan.
Under a suggestion of Sullivan. Very good. But anyway, I think now the terminology caught on. Yeah. So this is very good, because it actually now fits perfectly in the framework of in the Moore-Cartan framework that I was talking about before. So this problem that a priori you look at this and maybe you don't even consider that this is a deformation problem. Maybe it doesn't look like a deformation problem, but it is, and this problem is expressible, lives in G of P infinity H. So let me make this a bit more concrete. So we know that infinity structures live in here. So what about how they are related? Well, this is given by a theorem of Dotsenko, Shadrin, and Valette, who characterized this pi0 of the Moore-Cartan space by essentially saying, well, we already know that how to write this. So the exponential group of G P infinity A acting on the Moore-Cartan elements of exactly the same Lie algebra, P infinity A is just equal to, well, here we know that these are P infinity structures on A, and this action is by infinity isotopies. So so in particular, it tells you that in the quotient by the gauge action, you read exactly this problem. So whether two infinity structures are isotopic. And I wanted to, so this is a really nice result. And I want to point out that it uses it uses some really interesting techniques that are not available for every so I will not prove, but let me just say that the tools are really important that come into this. So you make use of the fact you want to do exponentials, right? Exponentials are easy, and exponentials are easier if you're dealing with an associative algebra, because it is an actual exponential. And these algebras are not Lie algebras, but they do come with a product. So this, as I mentioned yesterday, is a pre-Lie algebra, and with pre-Lie algebras, well, you have a product that is not associative. You can form so-called pre-Lie exponentials, and the formula is more or less what you would expect. So e to the power, so I denote by star the pre-Lie product. What do I say? Sorry, it's not e. So lambda, an element of the gauge group to the power 3, well, is lambda star lambda star lambda. You just need to choose. It's not associative, so you need to choose a parentization. So you always choose. Sorry. You always choose this parentization here, and then you can form exponentials. It turns out that you can do a lot of things making use of this pre-Lie structure, which allows you to prove results such as this one. And also it benefits from another fact, which is that so this plus the pre-Lie operad is isomorphic to an operad of rooted trees. So this is a result from Chapoton and Livernet. And in fact, this is really nice, because for the purposes of this pre-Lie deformation theory, you actually use the combinatorics of trees. So in a way, that's what gives you a good grip on everything that's going on there. Okay. So now let me take a particular case of this isomorphism, of this quasi-isomorphism problem, which I will frame it in terms of rational homotopy theory, which is, we saw yesterday in Alexander's lecture that so in rational homotopy theory, we consider this this functor of forms and the question could be why not to consider instead C star of X, so the simplicial or the singular cochains on this guy. Well, this guy is still an algebra, and the problem is it's an algebra that is not associative. It's not associative, not commutative. But one might ask, is it still somehow strong enough to retain the full homotopy type of the topological space X? So concretely, if I have a space X that is modeled by omega of X, well, we did see yesterday that this is quasi-isomorphic as an algebra, as an associative algebra to this. And well, imagine that this is also, so suppose that this is also quasi-isomorphic to a model of some other space Y. Now, the question is, does this imply that so that X is rationally equivalent to Y? And if I'm really not careful putting some adjectives, it just looks, well, equivalence relations kind of composed by definition. So you would say that, well, omega X is equivalent to omega Y, which is the same as X being equivalent to Y. Now, the problem is an algebraic one. So the problem that is underlying this question here, and maybe the reason why we don't teach rational homotopy theory in algebraic topology in the masters, is if I have A and B commutative algebras, is it true that their associative type characterizes their commutative type? So if A and B are quasi-isomorphic as as associative algebras, is it true that they are quasi-isomorphic as commutative algebras? Because if so, then this is true. And the theorem that we proved with Dan Peterson, Peterson, Daniel Robert Nicou, and Felix Viestra, kind of or inspired by works of Bashar Saleh, who proved it for H equals for A equals the homology of A, for A equals the homology of B, is yes. And I need to. So you said I stop at 45, right? More or less. Yeah.
I have a question.
Yes.
So far, we've been to detect the rational homotopy type of the space. Alexander was considering the PL omega.
Sorry, Alexander was considering?
Alexander
PL forms.
PL, which is your omega.
Yes.
Here you use the singular cochain. Your
Yes.
C star is singular, right?
My C star is, I mean, yeah, it depends if what you're modeling your spaces by. But say if your topological spaces are actually topological spaces, right, then say singular, yes.
And if you take a simplicial set, just take the normalized cochain, or would you take?
Yeah, but anyway, all of those are quasi-isomorphic as associative algebras. So
Not normalized, just cochain.
Okay. Yeah, but so yes.
Okay, this is that.
Right. So I want to yes. So yes, very good. Yes, for characteristic of k equals 0. So in fact, also rational homotopy theory works for any field of characteristic 0. We kind of just pick rationals because they're the most smallest one. But in fact, I don't know, part of other kinds of work I do is actually working with real homotopy theory when you work with the real numbers. The theory doesn't change almost anything. There's just some tiny things that change a bit. Right. So the reformulation that I presented to you before is the following. Reformulation from before gives us a reformulation of the problem. Tells you that if you take remember that we can consider this Lie algebra that gives us the Harrison complex. So C infinity on A, but here I see yeah. So I take this this C infinity of A, and Mark-Cartan elements here are just C infinity algebras on A. And what I can do is there is a map of Lie algebras that I mentioned also earlier today, that I can map this into A infinity. So under this map, a Mark-Cartan element, so a C infinity algebra is just mapped into its underlying A infinity algebra structure. And so what's our hypothesis here? We actually have alpha and beta that are two C infinity structures. So that I will just abuse notation and write the image by the same name. And our hypothesis is that they are quasi-isomorphic, so infinity isotopic. And under the interpretation of Spirley deformation theory, this is the same thing as there exists their gauge equivalent. So there exists gamma, a gauge that, but as a infinity algebras. So the question now is, can we get from here? Can we get from here? Can we deduce a gauge equivalence at the level of C infinity algebras? And well, the first question one might want to ask is, I mentioned this Goldman-Milson theorem that gives us kind of a result in this direction. So if those two Lie algebras are quasi-isomorphic, then Goldman-Milson tells us that that elements up to gauge equivalence, they are the same. But well, this is that map is injective, and it's injective in cohomology. This is a very classical result, but it is definitely not ever a quasi-isomorphism. So this Goldman-Milson theorem isn't strong enough to bias anything. So here, but there is some refinement that one can try to do, and the refinement comes in the form of the following actual theorem that, once I restated this, is the thing that proves the result. So theorem, if I have so what's our situation? Let G be a DGLA, and let's assume that it's complete as usual. And we have H, just something that injects in here. And now suppose H is a retract of G. But so H, a retract of G as what? As H modules. So H mapping into G, we can see, well, G is not only a module over itself as Lie algebra, but given a map, it's a module over H. So more concretely, this just means that i.e. there exists a map R from G to H. So that's so if I do first H, sorry, if I do first this and then I go back to H, I get the same thing. So essentially, R restricted to H is the identity on H, and it's compatible with the H module structure. So R of so let me denote by H an element of small h and X an element elsewhere. So this should be such that we have this property here. There is an X for H in H and G, what am I saying? And X in G. Then we actually have what we wanted. So then the Mark-Cartan element, the Mark-Cartan set of H, well, of H, well, it always maps into the Mark-Cartan elements of G, even up to gauge equivalence, but this remains injective if under this hypothesis. So is injective. So in other words, two elements arising from the beginning are only equivalent in the target if and only if they were equivalent from the start. So I should just point out that the proof of this result is not just you take this gauge on the right-hand side and you just take R of it and map it there. So there is actually some recursive construction, some iterative procedure to construct the gauge here that gives the appropriate result. So in particular is a priori not completely constructive, but actually all of this story fails from some lack of constructivity already from the start, from the homotopy transfer theorem, that you kind of need some explicit retraction data to get explicit formulas. But at least we can know conceptually that it exists. So I guess the question one needs to ask still is why is this this guy here in the situation, in the hypothesis of the theorem? And so So to deduce that G of A infinity A retracts to G of C infinity A. I guess, yeah. So A here was always supposed to be the homology. I apologize for this. It is something that is still worth pointing out, that in the pre-Lie deformation story, it's even if you have a differential, it's still only the infinity isotopes. So somehow testing that something is an isomorphism is much more manageable than testing if something is a quasi-isomorphism. This is not a problem here because so what I said before is we always reduce down to H, but so I actually wanted to write H all along. I apologize. So how do you deduce that this big Lie algebra retracts into this as an H module? This also follows from another operatic argument. So this follows from the fact that the map of operats Lie into the associative operat retracts as an infinitesimal Lie bimodule. So maybe let me just spend a few words, but not write much more. The point is that from so this is made. This uses co-Lie, the dual of Lie, and this uses the dual of the associative opera. So that's why this plays a role. Plays a role in this story. So we build directly. So it's something very universal. You build directly something at the level of operats. Now, what one might know is that PBW allows you to identify the associative operat in principle as a right Lie module as something of the form com-circ-Lie. This can be slightly enhanced to be made into well. First, maybe let me just say that as becomes a Lie bimodule by just again restriction of scalars. And okay, you can slightly enhance the PBW theorem to have an identification like this at the level of infinitesimal bimodules. So at the end, the retraction is really just you project something that looks like the symmetric algebra on Lie back to Lie. So this part is very explicit somehow. So okay. So this concludes the proof of the theorem, and tells us that that we can model, in the particular case of rational homotopy theory, we can model spaces by their cochain algebras. So I'll just spend the last minutes. First, any questions about this? Right. Yes, exactly. So maybe some people would argue from the start that cochains, these are anyway homotopy commutative, and even if they're not commutative on the nodes. So maybe one considers some sort of infinity or C infinity structure on them, and then but then it's a bit devoid of content. So the point is, if you forget this symmetry part, it turns out that you you still get you still retain at least all the notion of being homotopy equivalent. I am not saying anything about the full structure of the model categories of commutative algebras into the category of associative algebras.
I might not understand. Conceptually, I might not understand. I mean, algebraic topology tells us, oh, we need to consider E infinity higher homotopies for commutativity. And you come today, this morning, fresh, happy, and you say, no, forget all that shit. We just need to look at the associative, the cup product from singular cochains, and that's it. Wow.
Yeah, more or less, not really.
No, I did.
Yeah. Right. So Bruno asks whether whether one can just get rid of all rational homotopy theory and
No. Why conceptually I don't understand why you don't need all the commutativity, higher commutative. You see, they are all in some sense. You see, they are all included inside the associative product.
No, but it's different. So only the rational homotopy types are encoded. So not the full rational homotopy theory. So in some sense, you have, first of all, if you think about rational homotopy theory, is given by something that sends you from simplicial sets into the commutative algebras. And the whole point of Alexander's talk is a bit that this is an equivalence. Now, of course, this injects into associative algebra. So what we're saying here is something at the level of so these are infinity categories, and you can ask what happens at the level of, for instance, of all homotopy groups, in particular at the level of mapping spaces. So under this interpretation, our theorem it still does not say that much. So it tells you only when two things are equivalent. So it does not tell you. And also there is a problem that if you could just land in associative algebras, well, this is an equivalence, but this composite has zero chance of being an equivalence. So already you would have to restrict this to an awkward category, which would be associative algebras that actually are quasi-isomorphic to some commutative algebras, which is not even equivalent to having a commutative homology. Yeah, so there are problems at various steps. This awkwardness, I think, actually is one of them, even though it's maybe not the most imperative one. But there's just other questions concerning the rest of the infinity category of yeah. So let me use just the final minutes to talk about an application of to classical algebra, which I just find it very, very amusing. Which is that there is this open problem that you probably will only see it talked about in the archive sections like rings and algebras, and which is the following: if you take G and H Lie algebras, but so ungraded, like in a classical sense. There is this question of whether it is true that if you take their respective universal enveloping algebras, U of G and U of H, if it is true that this being isomorphic implies that G and H are isomorphic. Now, depending on the adjectives I put, this can be a triviality or a very hard problem. So if I think, well, universal enveloping algebras, these are Hopf algebras. They are bialgebras. They have a product and a coproduct, and you can always recover the Lie algebra structure from G by taking primitive elements with respect to this coproduct. So stated like this, I mean, in characteristic 0. So actually, by the way, the problem is completely, the implication is completely false in positive characteristic. Examples of dimension p plus 2 can be constructed. But so the question is, I don't actually want to remember that these universal enveloping algebras are Hopf algebras. I want to take just the actual definition of the universal enveloping algebra, which is an adjoint. So the target is really associative algebras. So if I have these two universal enveloping algebras that are isomorphic as associative algebras, is it true that the corresponding Lie algebras are isomorphic? Now, this is some people call this the isomorphism problem for Lie algebras, and it seems that this is a very complicated problem, despite how easy it is to formulate it. And now we can try to generalize this problem. Sorry, generalization to make it more homotopical in some sense. So GH now DGLAs, and you can ask whether UG quasi-isomorphic as associative algebras to UH is equivalent to G quasi-isomorphic to H as Lie algebras. Well, of course, then if you restrict to no differential and maybe no degree as well, you recover exactly the same problem. But actually, already here there is something funny happening, that in the other implication is not entirely trivial. So this is actually given by the PBW theorem that tells you that the universal enveloping algebra is a symmetric algebra. I mean, at least as a chain complex. And the symmetric algebra functor does preserve quasi-isomorphisms, which again is also something that only exists in characteristic 0. But what we can show is an incomplete version of this equivalence, which is just a direct corollary of the theorem that has the word yes there. Corollary of CPRW. So if G is, let's say G and H are nilpotent, then the result actually holds. U of G equivalent to U of H as associative algebras actually does imply that G is equivalent to H. And here it's, so G and H are DGLAs, and it's nilpotent in the graded sense. So if you restrict to classical Lie algebras, is graded nilpotent, but it's classical nilpotent, but it's this graded nilpotency that's, it only matters what happens degree by degree. So in particular, if they're concentrated in degrees at least 1, everything is nilpotent. And the proof of this now becomes just almost an exercise in this operatic business, in this operatic calculus, because the idea is that here we're interested in the preservation properties of a forgetful functor, whereas here we're interested in the preservation properties of a universal enveloping algebra functor. So it's an induction functor. It turns out that causal duality between Lie and commutative algebras interchanges the forgetful functor with the causal duality with the universal enveloping algebra functor. And that's more or less all that that we need. So let me give you the proof of this fact. Maybe I'm optimistic that this is very short, but maybe I'll still take some space to write it out. So what's our assumption? Our assumption is that I have UG, which is quasi-isomorphic to UH. So let me just write again. This is as an associative algebra. So what I can do is I can resolve G as a Lie algebra. There are canonical ways to resolve G as a Lie algebra. I can use this bar-co-bar resolution. Let me make this a bit more precise. So bar of G is something that gives you back a co-commutative co-algebra, co-nilpotent co-commutative co-algebra. Let me write bar com for that. And the co-bar construction gives you back a Lie algebra. And well, you still have the universal enveloping algebra functor over here. Now, actually, from the first implication of that theorem, the easier one, we know that this is a quasi-isomorphism. So it means that the full thing, U of a quasi-isomorphism, is a quasi-isomorphism. So it's already funny that we're kind of using the other implication to prove this. Now, if you forget about differentials, the universal enveloping algebra of this, well, this is a free Lie algebra. So the universal enveloping algebra over free Lie algebra is the free associative algebra, just because composition of adjoints is an adjoint, and you check that the differentials give you exactly that this is this is the associative bar construction, co-bar construction, sorry, of this bar com of G. So we do the same thing on the other side, and we conclude that here we have omega associative bar com of H. Now, you kind of just, so here as associative algebras. Now you kind of want to just cancel out these two, which you can. So compose with bar S, and we know that the bar construction of the co-bar construction is the identity. So we do this and we conclude that bar com G is bar com of H, and this is quasi-isomorphism preserving. But now, in principle, this was living in the category of associative algebras. This lands in the category of co-associative co-algebras, co-nilpotent. So this will only be an equivalence as co-associative co-algebras. But now, from essentially the dual theorem of that thing, well, we have two things that are co-commutative co-algebras there. So you can actually use, I don't know, CP RW, and you conclude that bar com of G is co-commutatively quasi-isomorphic to bar com of H. And here, finally, you would like to just cancel these guys out. There is a slight caveat, which is that, so this is not a direct map, so you need to be a bit careful when taking co-bar constructions. So co-bar constructions don't preserve all quasi-isomorphisms. So so there is a slight technicality, but here you use, since nilpotent, use the nilpotency, you can conclude that indeed G is quasi-isomorphic to H now as commutative algebra. Definitely not as a commutative algebra. Sorry, only as is causal self-dual as a Lie algebra. So you ruined my, I ruined my punchline. No, so it's really nice, and I would just, so now that I'm over time, way over time, I'll just take 1 second to appreciate that this is in principle partial resolution to a problem that in principle only lives in classical algebra, that so far all proofs that are known only, so this one, so it's not a full proof of this, but it's a partial proof of this, and it's a proof that necessarily requires you to go to a homotopy setting. And a priori, this is a talk about lecture series about deformation theory, and one looks at this and it really does not look like anything that has anything to do with a deformation problem. So I'll stop here. Thanks.
Thank you very much.
Yes, I will repeat the questions for the audience.
I just wanted to add about the status of this problem for extracting methods. As far as I know, it was only known for nilpotence algebras up to dimension 6 with computational proofs.
Right. So the remark is that okay, maybe I'm underselling it a bit and saying that it's only a partial proof. In fact, it was only known for essentially algebras up to dimension 6, you say, Daniel?
Yes, nilpotence up to dimension 6.
Okay, by computer computations.
And is there the representation where it has the
Right. Right. Also, the fact that yeah, that this is false in characteristic P kind of yeah, indicates that there shouldn't be an extremely naive proof of this in general.
And regarding the other problem, we don't know if it's true characteristic P. I have to expect it to be false.
Yeah, I really think it should be false. I would bet a lot of money on that.
No.
But not money. I would bet for Portugal tomorrow against France. Yes.
We're qualified. We're happy.
Yes. Yeah, no, but I mean, there is yeah, there are some results. Yeah, but I don't know. I cannot say that I can prove that this is false in characteristic P, but I don't expect it. Yes.
So for the deformation complex, we actually use the coordinate to make the copart construction, like to present the infinity. And I was wondering if there is a like an intrinsic notion of deformation complex, like just yeah, without using the just infinity.
Without using the cooperate, just P infinity.
Yeah, like just a cooperate resolution, but we don't know what it comes from.
Well, first, all cofibrillant resolutions, they're not all bar cobar, but they're all retracts of cobar algebras. So there is that, and then well, if you can do so I mean, I guess you can ask the more model theoretical question, which is you have say a P algebra. You don't know what P is. You don't know a cobar simple cobar expression for P infinity, and you have B another P algebra, and you can just ask what is the mapping space. So so up to homotopy equivalences from A to B, and well, in this model category, everything here is fibrant. So at the end, you find yourself trying to resolve A. It just turns out that these things are much more manageable if you have a cobar expression, which gives you so. There are two bar cobars here, right? There's bar cobar at the level of operats, and then this descends to some bar cobar at the level of algebras. And it's just a very good framework to express this, but in principle, nothing prevents you from trying to do this sort of computations. But I mean, it's functorial, it's very good, and that's, I think, why people use it.
I will say something, anywhere you refer to quasi-free on. So in quasi-free Operadic that you take to resolve, the generators form the homotopic Operadic. Plugging into this construction, you get an infinity algebra. And this ultimately shows that whichever model you take to UP, the depth complex you get, they are all quasi-isomorphic as an infinity algebra. So in some sense, there is a uniqueness property of this guy. And which one you choose, when your opera is cosud, this is minimalistic.
Right.
And he enjoyed very much the fact that it comes from a co-Operadic, and then he was able to use the pre-calculus.
Right.
Very crucial for him.
So just to say in a few words what Bruno just said. Yeah, essentially there's only you could essentially just always take the bar cobar construction of an opera. This gives you always like a cobar form of your opera, and in principle there might be many of them, but they all end up being quasi-isomorphic because precisely the deformation complex is functorial and preserves quasi-isomorphisms of operas. So if we can equivalently take any one possible, might as well just take the smallest possible one. And when you're in the framework of causal duality gives you a completely optimal answer to this by providing, well, it's essentially the case when B of P is formal, so it gives you the smallest possible coopera to put there, which is very useful for computations.
Is there any other question? You can also chat around coffee. Ask if there is any question online.
Is there any question online? Right.
I don't think so.
Oh.
Okay. So let's Ricardo, let's turn Ricardo again.